Hello, and welcome to today's SI video, where we're going to be talking about transporters. We're going to go over what they do, how they do it, and where they do it. So at the simplest level, this is a cell. Transporters serve to bring things into or out of the cell, and this is for things that can't normally cross the plasma membrane, so large molecules or hydrophilic molecules that can't diffuse across the lipid bilayer. And if we look more closely, imagine this is a lipid bilayer. We'll draw in just kind of a generic transporter here. The first type of transport we're going to go over is passive. And this means that no energy is required. Molecules just move down their concentration gradient. So if you have drug molecules out here, a lot out here, very few in here, this transporter is going to facilitate their passage into the cell. And usually this is done using conformational changes. So if you look over here, it'll start with an outward open conformation. You'll have your drug molecule out here. It'll move in, bind to a central site on the transporter, and the transporter will then shift to a conformation much like that, an inward open conformation, drug molecule still in the center, and this will allow it to move into the cell. Just for context, we still have our bilayer here. This is outside, and this is inside the cytosol. And these ones that do passive transport are generally bidirectional. So if you end up with a much larger concentration of drug on one side, the transporter will reverse direction and start moving this. So these rely solely on concentration gradient. And now, if we go ahead and talk about active transport, they happen at the same location. You have a cell membrane, but this time it requires energy to move it across. And there are two kinds, primary and secondary active transport. So if we talk about primary active transport, this is molecules that directly consume ATP. So you have your transporter in the membrane, and usually there are two ATP binding sites on the inside, one on each side. So you have ATP that binds there and there. And these transporters are almost always pointed out of the cell. So for orientation, we have out and in here. And so what happens is these usually work on hydrophobic drug molecules that can diffuse through the membrane. But as they diffuse, some make it through, but some hit the transporter that's membrane bound, end up in here, and get pumped back out with the consumption of ATP. Good examples of this type of transporter is P-glycoprotein, is probably the most common, and you'll find this in the gut and the liver and the blood-brain barrier. Now, if we want to look at secondary active transport, these don't consume ATP directly, but rather they rely upon a chemical gradient that exists but not for the drug molecule. So if we have our membrane, again, outside, inside, and we have our transporter, and these are called co-transporters. And so here, let's say we have our drug molecule out here. We can also have sodium ions. And if you remember, sodium concentrations are high outside the cell, low inside. Potassium is high inside and low outside. And so what this will do is it will use the sodium gradient. There's a lot out here and a little in here. So sodium is going to want to move into the cell. And this is going to take that energy to use this to bring the drug molecule in as well. So it'll be one drug molecule with one sodium is common, but sometimes you also see two sodiums for one drug molecule. And this can move drug molecules against their concentration gradient as long as it's not too big and as long as the sodium gradient exists. And this is called secondary active transport because there's active transport consuming ATP over here that keeps pumping the sodium out of the cell to maintain the gradient. And so it's secondary because it's using energy that was already committed to the electrochemical gradient of sodium, but that used ATP elsewhere. And common examples of transporters that do that is PEP-T1 in the gut, which brings dipeptides in using the hydrogen in the gut. Of note, these transporters, it doesn't have to be sodium, it can be hydrogen, it can be potassium. And in the gut lumen, you have a high concentration of hydrogen from the stomach acid, that is used to transport in dipeptides in the intestine. But those transporters are also important for antibiotic absorption. And if you think about where in the cell these transporters are, there's always going to be in the cell membrane, but cells generally have two sides. So now this line represents a full cell membrane, and this is the apical, and this is the basal side. And so if we're looking at the gut, so we'll call this the GI tract, you have your apical side and you have your gut lumen. So this is where food is. This is cytosol. And this is blood down here. And so if you have a transporter in here that's bringing drug molecules in, let's say that this is a passive transporter, so they're just diffusing across their concentration gradient, then this, in theory, you would only equilibrate to 50%. However, once the drug is in here, it can diffuse into the blood, and because the blood is flowing away, this concentration stays at or near zero, which allows the continued absorption of these molecules through the transporter. However, if you were to have a compound that blocks this transporter, these molecules can no longer get in, and your concentration in the blood decreases. So this would decrease your exposure to the drug. However, if you had an efflux transporter that is taking these drug molecules and pushing them back out, if that is inhibited, this then allows these molecules to make it through into the blood, and your concentration will increase. Now, one thing that we'll note is that the basal side of transporters is always blood. And the apical side is always a lumen. So in the GI tract, that's the inside of your intestines. Sorry, let me get this cleaned up here. So we have our basal and our apical, and this is always going to be blood, and this is going to be lumen. But if this is now not a GI cell, but a liver cell, this lumen is bile. So this is the bile duct. So this is leaving the body. And the blood is things that are already in the body. So here transporters would serve to move things out of the body. So if you have your drug molecules already in the blood, then you can have transporters in either side. Export transporters like PGP that use active energy are almost always in the apical side, but other ones, especially the passive transporters, can be in either membrane. And so here, the transporters serve to allow it into the liver cell and then to pass into the bile where it is excreted from the body. So in this case, if you have something that blocks a transporter here, it's not going to allow the molecule to leave the body, and therefore your concentration in the blood is going to increase because you either can't metabolize it in the liver or can't excrete it into the bile. And so here, whereas in the gut, something blocking the transporter would decrease plasma concentrations, here it would increase them. Of note, active transporters like PGP are always going to be exfil transporters, and so blocking those will always increase a drug concentration, because in the GI tract it will allow more absorption, whereas in the liver it will prevent excretion. Okay, and I think that is all we have for today. Thank you.